Okay, we're looking at the last part of your notes here today, and we are going to be solving some root equations. We're going to start today just with square roots. All four of these that you see on the screen are square roots with things being added, subtracted, and they equal something. The first thing you want to do, if there's only one radical in the problem, whether it's a square root, a cube root, or a higher power root, you want to isolate that root, get it by itself. So again, the first thing we're going to do is make sure that that root is by itself. So on the first one, that's taken care of for us. After you do that, then you're going to get rid of a square root. And hopefully we remember to do that. You simply square. If it's a cube root, you're going to cube. And you're going to do that to the other side as well. Whether there's one term or 5 terms over there, you're going to square it. Then we know that a square will cancel out the square root, so we get the x minus 5 to drop out there. And 2 squared happens to be 4. And we add our 5 over, so we wind up with 9. It is imperative on these root problems that you check your answer, because you will have extraneous solutions just like we did in the past with absolute value. Literally you're going to plug that back in. That will be the square root of 9 minus 5. Whatever that is supposed to equal 2. Well, we know 9 minus 5 is 4, and the square root of 4 is 2. So it checks this is a solution. We've got the graphs on here to let you see these graphically what's happening as well. We know we could graph y equals root x minus 5, and we can graph y equals 2. Graphing the left side as one line, the right side as another. And, well, I say line, this is a function. It's not going to be a line. But we know that that's going to be over at 5, and we know what our parent function looks like. So it's going to be this graph here. And y equals 2, remember, it's been a while since we've dealt with that, but that is a line, and it is a horizontal line that goes through 2. So you are looking at this. The solution is that intersection. They intersect at the point 9, 2. The x value is your solution. So we got 9 here, we got 9 as we solved. So we know that we've done it right. We're going to try this other one. We're going to graph first. This side, when I graph that, it moves to the right 4 and up 7. And it's no stretches or compressions. So it's going to look like this, going off to the right. This side, y equals 4, is going to be this line down here. Well, hopefully you see there is no point of intersection between those two, so there is no solution based on the graph. We can do the empty set sign, or you can simply write no solution. Either's fine. Let's see algebraically why that happens. First thing we would do is we would subtract the 7, and we would get the square root of x minus 4 is equal to negative 3. Again, hopefully that throws up some big red signs. You know you can't take the square root of something and get a negative number. So if at this point you recognize that negative number, then you could say no solution. If you don't, you may continue. You can still solve the problem. That would be squared. This would be squared. We get x minus 4 equals 9, because negative 3 squared is a positive. Then I would add my 4, so I get 13. However, when I go check that, 13 minus 4, well, that's 9. Square root of 9 is 3. This is still supposed to be adding 7. And 3 plus 7 is 10, not 4. So it doesn't give you a true statement. It's not a solution. All right? Looking on at the bottom, same concept. You want to get the radical by itself, and then you want to square both sides. This radical is by itself, so I can square. I've got to square the binomial x plus 3. So I highly recommend you need to write that out a second time. So on the left, we're going to get x squared plus 25 because the square cancels off the radical. Over here, though, you've got to distribute. So we get x squared, we get 3x and another 3x, so that's 6x, and we get positive 9 at the end. It appears to be a quadratic because there's x squares in there, so we're going to subtract those, get them on the same side, but the squares cancel out, so really you're looking at a linear equation. You just want to get that x by itself. Subtract your 9. 16 is 6x. Divide both sides by 6. So x equals 16 over 6, which reduces to 8/3. Again, may not be a solution. We've got to plug it into C, even when it's ugly. So when I plug that in, 8/3 squared is going to be 64/9 plus, I went ahead and turned 25 into ninths. 25 times 9 is 225 over 9, and that's going to equal 8/3 plus 3, and I went ahead and made that 9/3 so that I could combine my like terms. The right side is 17/3. On the left, we wind up getting 289, which hopefully you recognize is a perfect square. And you get square root of 9 on the bottom. 289 is 17 squared, and 9, of course, is 3 squared. So this one does check. All right. On number 4, as you start looking at this, be careful. I made the mistake of not paying attention to the fact they gave me a perfect square. You can still do the problem, though, even if, first thing you would do is subtract the 7, and then you could square this side, even with a radical in it. You just have to work it out. But since that is a perfect square, I'm going to make that be 2, and I'm going to say x minus 4 equals negative 5. I hope you remember to go ahead and stop at that point. If you don't, we're going to square, so we get x minus 4 equals 25. So x is supposed to be 29, but if I plug that in, 29 minus 4 plus 7 is supposed to equal, I'm going to write a 2. That winds up being 5, because that's square root of 25, plus 7 is not 2. So it is not a solution. It is extraneous. And that is the expectation. However, if you catch it up at this stage and you say, hey, I realize it's no solution, that's okay. Perhaps circle the negative or something so we know why you think so. But other than that, you do need to label the 29 as extraneous. All right. On the back side, we're just going to look at 2 more. Number 5, when you look through this one, it is not by itself, so we are going to subtract that 5, and then I'm going to square both sides. I do have x minus 5 twice, so make sure you're distributing. The left side just gives you the x minus 3, but on the right, I'm going to get x squared minus 10x plus 25. It is quadratic, so I'm going to go ahead and get it equal to 0. So I will wind up with x squared minus 11x plus 28. That does factor, so we get x minus 7 and x minus 4. Each of those are going to be set equal to 0 in order to solve, so we wind up getting x is 7 and x is 4. I do have to plug both of them separately in, so when I check 7, I'll get square root of 7 minus 3 plus 5 equals x, which is 7. So 7 minus 3 is 4, which is 2 plus 5 does equal 7. So that is a solution. For the 4, I'm doing the exact same thing. I'll say 4 minus 3 plus 5 is supposed to equal x, so that is 4. That winds up being root 1, which of course is 1, plus 5 is not equal to 4, so this one's actually extraneous. That would be an expectation here, that you would label the 4 as extraneous and that you would have that, because you couldn't find the 7 without finding the 4. We're going to skip 6. You do basically the same thing. The only thing that happens on that one is you wind up with imaginary solutions. I'll show you the answer on that one. Number 7, this one has 2 radicals in it, and the first thing you're going to want to do there is separate those radicals. So I'm going to add the negative one over. So now I'm going to square both sides. It's not ideal because you still have a binomial, so you still have 1 plus root x minus 1 that you're multiplying that by. You're going to distribute. But when you square on the left side, that radical does go away. So basically the idea is you separate them, you make one of the radicals go away, and then you do the whole process again. I'll wind up with 1 radical on the right, I'll get it by itself, and square both sides again. As I multiply out here, I get 1. I wind up getting 1 root x minus 1 and another 1, so I'll get 2 root x minus 1. And when I multiply it times itself, that's just an x minus 1. Alright, I need to get everything on get my radical alone, so I'll subtract my x, which conveniently subtracts that x. My minus 1 will cancel out my positive 1, so really I've got 3 equals 2 root x minus 1. You've got a choice. You can divide both sides by 2, or you can square each of these 3 pieces. Square the 3, square the 2, and square the root. Either way is fine. Let's go ahead and just square everything so that hopefully you won't remember or won't forget if there's a number outside your radical, you have to square it. That winds up giving me 9 and 4 times, because this 2 is times the root, so that's 4 times x minus 1. You can either distribute or you can divide both sides by 4. Probably, since I did it this way, I would go ahead and distribute the 4. And so I'm going to have 13 equals 4x, or x equals 13 fourths. Again, this is what I've got. I do have to check it. So when I plug that in, that's going to be 13 fourths plus, I'm going to turn my 3 into fourths, so that'll be 12 fourths, minus 13 fourths again, same x, minus 1, which is going to be 4 fourths, is supposed to equal 1. Well, this winds up being 25 fourths, which is 5 halves. This winds up being 9 fourths, which is 3 halves. And 5 minus 3 gives you 2 halves, which is indeed 1. So it works. Okay, I'm going to show you the answers to 6 and 8. Actually, I don't have 8 worked all the way out, but feel free to work through those if you'd like. You can stop the video if you need. I did stop on number 8 because it's huge numbers. The same concept applies though. And like I said, 6 is imaginary. Alright, on the next video, we'll actually deal with powers higher than square roots. And we'll look at rational exponents, or fraction exponents. As you can see, that happens on 9 and 10. Thanks.